Hi dear students, today we start our discussion on the electric field due to continuous charge distributions. The last class we discussed the electric field due to discrete charges, and today the electric field due to continuous charge distributions. Continuous charge distributions means we have different types of the charges. First one is line charge distribution. That is, here we will find the electric field due to this line charge distribution. Before going to the discussion, I would like to recall one thing, that is, if a charge Q that is kept at a distance r prime from the origin of this coordinate system xyz, and the electric field due to this single point charge at this point P, that is, this point P is at a distance, that is, this distance is r, here r, charge is at the single point plus Q charge, and if so, the field point P, which is at a distance separation vector r, that is, this will be difference between r and r prime. This is a point of interest where we are finding out the electric field due to this plus Q charge. That electric field we have already written. That electric field was 1 by 4 pi epsilon 0 Q divided by separation vector r square r separation vector r cap. Okay. Now, if the charge Q is at the center means at the origin, then the separation vector Q is here, r prime is equal to 0, that is, this quantity is 0, therefore the charge is situated at the origin. Then the point of interest P, that is at a distance r, that is, this r in this figure. Okay. In such case, the expression for the electric field, that is, here the r prime is equal to 0, then separation vector r will be equal to r, then this expression will be reduced to this form, that is, instead of separation vector r, we will substitute r equal to r, then electric field will be E is equal to 1 by 4 pi epsilon 0 Q divided by r square r cap. This was the normal representation, which means this is the special case of this situation. In this today's discussion, I consider that all of the line charges distributions which are kept at the origin of the coordinate system, whatever be the line charge distribution, whatever be the surface charge distribution, and also the volume charge distribution, all are kept at the origin. Therefore, the field of point, that is the point P, which is at a distance r from the line charge distribution. Therefore, I will use this notation, that is symbol r, for the representation of the distance in the expression for the electric field. Therefore, the line charge distribution means I have a wire whose line charge density is defined as lambda, that is dq by dl. This is a linear charge density. Then the unit of lambda is coulomb per meter, that is the unit of lambda. Then if I consider a small length element, that is dl, that it contains a charge dq, then this line segment is kept at the origin of the coordinate system. Therefore, the electric field at a distance r from this line segment, that is given by dE, because this electric field is due to the small line segment dl and charge dq. Therefore, the expression for the electric field I can write generally dE is equal to 1 by 4 pi epsilon 0 dq by r square, and if you write in the vector notation, this is r cap. Then from this expression I can easily replace this dq by lambda dl. Therefore, the expression for the electric field can be written as 1 by 4 pi epsilon 0 lambda dl divided by r square r cap. Therefore, the electric field due to this wall wire, that can be written as, if integrate this dE, that will be E. If you do the integration here, 1 by 4 pi epsilon 0 will be outside, and this will be 0 to L lambda dl by r square r cap. This is the electric field due to the linear charge distribution. In the second case, now we consider the electric field due to continuous surface charge distribution. That is, I consider a surface, that is a sheet that is positively charged, maybe somehow by conduction or induction. The electric field due to these surface charges, that is the charge contained on the surface, that is sigma surface charge density dq by dA. This is the surface charge density, charge per unit area. Its unit of sigma is coulomb per meter square. Therefore, the electric field I can write, that is, you know the expression for the electric field due to a dq charge, that is 1 by 4 pi epsilon 0 distance r dq by r square r cap. Then from this expression I can rewrite dq is equal to sigma dA. Simply here I can replace this dq by this expression. It is 1 by 4 pi epsilon 0 sigma dA by r square r cap, or net electric field due to this wall surface charge distribution, that is E is equal to the surface integration, integrate over the surface 1 by 4 pi epsilon 0 surface integral sigma dA by r square r cap. Now let us go to the third distribution, that is electric field due to volume charge distribution. That is, consider a particular volume that is somehow charged, maybe positively or negatively. Here I consider this as a positively charged. I need to find the electric field at a distance r. Then the surface charge density is defined as sigma, is charge per unit volume. This is a volume charge density. Then this dq can be written as rho dV. Expression for the electric field due to charge dq, that is 1 by 4 pi epsilon 0 dq divided by r square r cap. Then if you replace this dq by the above expression, then total electric field we can write 1 by 4 pi epsilon 0 into rho dV by r square r cap. This is the volume intake. This is the expression for the electric field due to volume charge distribution. Now let us go to the next topic, that is electric field lines. Now you are familiar that the electric field due to a single point charge, electric field due to a single point charge. This is a electric field due to a single point charge, where the plus q charge is kept here. The electric field lines are diverging away from the charge, and the electric field at a distance r from the charge, that is can be written as E. We believe that the charge is kept at the origin of the coordinate system, that is 1 by 4 pi epsilon 0 q by r square r cap. That is, I will mention here, situated at the origin of the coordinate system. Actually, what is the magnitude of the field? The magnitude of the field is indicated by the density of the field lines, which means if the field lines are closer, that is, if you look at this area, the field lines are closer. Now if you consider another circle, here the field lines are not closer, this is relatively far apart, but here the field lines are closer. That is, if the magnitude of the field, that is indicated by the density of the field lines. That is, if the field lines are closer, like this one, at that point the field is very strong. And if the field lines are relatively far apart, like this one, where the electric field is very weak. I will draw one figure. This is the region A. This is the representation of the electric field lines. And I will mark 3 regions in this. That is, this one is B, and this line represents the region C. A, B, C are the 3 regions in the electric field. Here we have to say where is the intensity of the electric field is maximum and where is the intensity of the electric field is minimum. Here if you see the number of electric field lines, or where the electric field lines are lying closer, that is, here if you consider a certain area, the number of electric field lines in this area is larger, therefore here the field strength is stronger, therefore the intensity of the electric field at the A is larger. If you compare the section area B, the region B, if you consider the same area, number of electric field lines is very smaller, or we can say here the electric field lines are relatively far apart, therefore the field is weaker. But if you compare to this region B, the region C is far better, because the electric field lines are very closer. Therefore, the intensity of the electric field is larger in the region A and is greater than in the region C and is very small in the region B. The strength of the electric field is larger at the point A than at C than at B. Now let us go to the next topic, that is electric flux. Electric flux and Gauss's law. Now let us first discuss what is electric flux. Electric flux is nothing but it is a measure of the number of electric field lines passing through a surface. Okay, it is nothing but a number. It represents how many number of electric field lines are passing through a given surface. That electric flux you are very familiar with this electric flux because you have already learned in the +2 classes that electric flux is defined as phi E, the surface integral of E dot dA. Let us consider a surface. In this surface, dA is the area vector that is perpendicular to the plane of the surface, and E is the electric field line. E dot dA means here the angle theta is the angle between the electric field and the area vector dA. How these electric field lines can be produced? If you keep here a charged sphere or some charged material, the electric field lines will be emerging away from these charges, and in that area we consider, in that region we consider an area whose surface area is S. Then the flux is defined as the total number of electric field lines passing through this surface. Now if you go to the deeper, that is, if I have a single +q charge, the number of electric field lines from this charge will be like this one. A closed surface, the number of electric field lines coming out from this charge can be calculated. Then if I keep more charges at the center, that is, I place one more charge here, another +q charge, then the number of electric field lines passing throughout the surface will be increased. That is, the number of electric field lines passing through the surface also increased. That is, if the flux through any closed surface, that is a measure of the total charge inside. Okay. That is the essence of the Gauss's law. That is, if I note here, flux through any closed surface is a measure of the total charge inside. If I keep more number of charges inside, the number of field lines, that is nothing but the flux coming throughout this surface, will increase. Flux is nothing but the measure of the charge inside the surface. The charge outside the surface will contribute nothing to the total flux. Okay. Now, consider a point charge Q placed at the origin of a sphere. Calculate flux of E through that sphere. Okay, let us do this as a question. What does it mean? That is, at the center of the sphere, a charge q is kept. Then we need to find the flux through the sphere. And that sphere of radius r is also given. Sphere of radius r. That is, the sphere have a radius r. We need to find the flux through the sphere. That is, we know that if we keep a charge like this one, either it may be plus q or minus q. If I consider this is a plus q, the electric field lines will be diverging away from this plus q charge. Large number of electric field lines will be there. Then the electric field, due to this plus q charge at a distance r, here I believe I consider that this electric field, this charge is placed at the origin of the coordinate system. Therefore, electric field due to this charge is 1 by 4 pi epsilon 0 q divided by r square r cap. And the electric flux, that is our aim, the surface integral E dot dA. Since it is a sphere, that is a three-dimensional object, I consider the area vector as a in spherical polar coordinates, that is r square sine theta d theta d phi r cap. And the E dot dA, I can substitute this E and dA in this expression. Therefore, this is a closed surface integral 1 by 4 pi epsilon 0 q by r square r cap dot r square sine theta d phi r cap. This r dot r is equal to 1. Then q by 4 pi epsilon 0, I can take it outside, is q by 4 pi epsilon 0 into, and here one more thing, it is very clear that this r square and r square get cancelled. Then this will be q by 4 pi epsilon 0. The integration from 0 to pi sine theta d theta, 0 to 2 pi d phi. Then the answer will be 1 by 4 pi epsilon 0 into, this will you give answer the 2, and this will you answer 2 pi, and this 4 pi will cancel out. Answer is q by epsilon 0. That is, the left hand side, that is phi, is nothing but the flux. The total electric flux through any closed surface, that is equal to the 1 by epsilon 0 times the charge enclosed by that surface. This is the Gauss's law. That is, if I write this equation, phi is equal to surface integral E dot dA. This is nothing but electric flux. Therefore, I will write phi E. Next unit, we will discuss the magnetic flux. In that case, we will write phi B. Okay. Since the electric, this is the flux of E, that's why you have mentioned E. This is equal to, that is q by epsilon 0. This is nothing but the Gauss's law. That is, the total electric flux through any closed surface is equal to 1 by epsilon 0 times the net charge enclosed by the surface. This is the net charge. This, if you see this picture, the total number of electric field lines passing through this closed surface, that is equal to the total charge enclosed with the surface. If I keep more number of charges, more number of field lines will pass out through this surface. Fine. That's the statement of the Gauss's law. I can write like this. Okay, that is the total electric flux through any closed surface is equal to 1 by epsilon 0 times the net charge enclosed by the surface. This is also called the integral form of the Gauss's law. Fine. We will do few problems based on this Gauss's theorem. Here the first question is one. A point charge Q is placed at the center of a cube of side A. Find the electric flux through a surface of the cube. That is, we have one cube. There is a charge is kept at the center. Now we have to calculate the electric flux through a surface of the cube. That surface is this one. ഏതെങ്കിലും ഒരു സർഫേസിലൂടെയുള്ള ഇലക്ട്രിക് ഫ്ലക്സ് ആണ് നമുക്ക് കണ്ടുപിടിക്കേണ്ടത്. അപ്പോൾ നമുക്കറിയാം ടോട്ടൽ ഇലക്ട്രിക് ഫ്ലക്സ് ഇതിൽ ഈ ഒരു ചാർജ് വെച്ചിരുന്നാൽ എല്ലാ ഭാഗത്തിലൂടെയും ഇലക്ട്രിക് ഫീൽഡ് ലൈൻസ് ഇങ്ങനെ കടന്നു പോകും. അപ്പോൾ ഈ ക്യൂബിന് 6 സർഫേസ് ഉണ്ട്, 6 ഫേസ് ഉണ്ട്. Let us define first phi. Phi is the flux through one phase. Phi നമ്മൾ ഡിഫൈൻ ചെയ്തിരിക്കുന്നത് ഒരു ഫേസിലൂടെയുള്ള ഫ്ലക്സ് ആണെന്ന് നമ്മൾ അസ്യൂം ചെയ്തു. നമ്മളവിടെ ചിത്രത്തിൽ കാണിച്ചിരിക്കുന്ന പോലെ ഈ ഷെയ്ഡ് ചെയ്തിട്ടുള്ള സർഫേസിലൂടെയുള്ള ഏതെങ്കിലും ഒരു സർഫേസിലൂടെയുള്ള ഏതെങ്കിലും ഒരു ഫേസിലൂടെയുള്ള ഫ്ലക്സ് ആണെന്ന് നമ്മൾ അസ്യൂം ചെയ്തു. അപ്പോൾ ഈ 6 വശങ്ങളിലൂടെയുള്ള ഫ്ലക്സ് 1, 2, 3, 4, 5, 6 വശങ്ങളിലൂടെയുള്ള ഫ്ലക്സ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ടോട്ടൽ ഫ്ലക്സ് through 6 face of the cube, it is 6 phi but q by epsilon 0. ഈ 6 വശങ്ങളിലൂടെയും കടന്നു വരുന്ന ടോട്ടൽ ഫ്ലക്സ്, that is the total flux coming out from the cube or from the charge, that is 6 phi q by epsilon 0. Then flux through one phase is equal to q by 6 epsilon 0. The next question idana, a charge q placed at one corner of a cube, find the flux through the cube. ഈ ക്യൂബിൻ്റെ ഒരു കോർണറിൽ ചാർജ് വെച്ചിട്ടുണ്ട് എങ്കിൽ ഈ ക്യൂബിൽ കൂടിയുള്ള ടോട്ടൽ ഫ്ലക്സ് കണ്ടുപിടിക്കണം. അപ്പോൾ ഇത്തരം പ്രോബ്ലം സോൾവ് ചെയ്യുമ്പോൾ പെട്ടെന്ന് നമുക്ക് ചെയ്യാൻ കഴിയുന്നത് ഇങ്ങനെ ഓർത്താൽ മതി. ഈ ചാർജിൽ കൂടെയുള്ള ഫ്ലക്സ് മൊത്തത്തിൽ ഇതിൽ കൂടെ കടന്നു പോകില്ല, ഇതിലൂടെ കടന്നു പോകുന്നുണ്ട്. പക്ഷേ ടു എൻക്ലോസ് ദ വോൾ ഫ്ലക്സ് കമ്മിങ് ഫ്രം ദ ചാർജ്, we need to calculate how many cubes are required. ഈ ചാർജിൽ നിന്ന് വരുന്ന എല്ലാ ഫ്ലക്സിനെയും കൂടി എൻക്ലോസ് ചെയ്യണമെങ്കിൽ നമുക്കിതിൻ്റെ ഇവിടെ ഒരു ക്യൂബ് വെക്കേണ്ടി വരും, ഇതിൻ്റെ അപ്പുറത്തൊരു ക്യൂബ് വെക്കേണ്ടി വരും അല്ലേ, കാരണം ഇതൊരു കോർണറിലാണ് കിടക്കുന്നത്. ഈ കോർണറിൽ കിടക്കുന്നത് കൊണ്ട് ഇത് 8 ക്യൂബുമായിട്ട് ഈ ചാർജ് ഷെയർ ചെയ്യുന്നുണ്ട്. Therefore 8 cubes are required to enclose the flux from the charge. നമുക്ക് 8 ക്യൂബ്സ് വേണം ഈ ചാർജിൽ നിന്ന് വരുന്ന എല്ലാ ഫ്ലക്സിനെയും കൂടി എൻക്ലോസ് ചെയ്യിപ്പിക്കാൻ വേണ്ടിയിട്ട്. അപ്പോൾ 8 ക്യൂബിൽ കൂടി കടന്നു പോകുന്ന ഫ്ലക്സ് ആണ് ഈ ചാർജ് മൂലമുള്ള ടോട്ടൽ ഫ്ലക്സ്. നമുക്ക് ഇങ്ങനെ എഴുതിക്കൂടെ, 8 into 5 that is equal to Q by epsilon 0. 8 5 എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ടോട്ടൽ ഫ്ലക്സ്, 5 എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ഫ്ലക്സ് ത്രൂ 1 ക്യൂബ്, ഫ്ലക്സ് ത്രൂ 1 ക്യൂബ്. അങ്ങനത്തെ 8 ക്യൂബുകൾ വേണം. Therefore flux through 1 cube, that is flux through 1 cube is equal to Q by 8 epsilon 0. ഇനി ഗ്രിഫിത്തിലുള്ള ഒരു പ്രോബ്ലം നമുക്ക് സോൾവ് ചെയ്യാം. ഇതാണ് ചോദ്യം. അതായത് എ ചാർജ് Q sits at the back corner of the cube as shown in the figure. നമ്മുടെ ചാർജ് ഇവിടെ വെച്ചിട്ടുണ്ട്, ഈ കോർണറിൽ നമ്മുടെ ചാർജ് വെച്ചിട്ടുണ്ട്. വാട്ട് ഈസ് എ ഫ്ലക്സ് ഓഫ് ഇലക്ട്രിക് ഫീൽഡ് ത്രൂ ദ ഷെയ്ഡഡ് സൈഡ്? ഷെയ്ഡ് ചെയ്തിരിക്കുന്ന ഈ സൈഡിൽ കൂടിയുള്ള ഫ്ലക്സ് എത്രയാണെന്ന് കണ്ടുപിടിക്കണം. ഓക്കെ, നമ്മൾ തൊട്ട് മുമ്പത്തെ പ്രോബ്ലത്തിൽ നമ്മൾ മനസ്സിലാക്കിയിട്ടുണ്ട്, ഈ ചാർജിൽ നിന്ന് വരുന്ന മൊത്തം ഫ്ലക്സിനെ എൻക്ലോസ് ചെയ്യിപ്പിക്കണമെങ്കിൽ 8 ക്യൂബ്സ് വേണം. ഞാനതിൻ്റെ ചിത്രം കാണിച്ചു തരാം. അതായത് ഈ ചിത്രത്തിൽ ഇത് നമ്മുടെ തന്നിരിക്കുന്ന ക്യൂബാണെന്ന് അസ്യൂം ചെയ്യാം. ഈ ക്യൂബ് ചോദിച്ചിരിക്കുന്നത് ഒരു സൈഡിലൂടെയുള്ള ഫ്ലക്സ് ആണ് കണ്ടുപിടിക്കേണ്ടത്. നമ്മുടെ തന്നിരിക്കുന്ന ഈ ക്യൂബാണ്, ആ ക്യൂബിൻ്റെ ആ സൈഡാണ് ഈ സൈഡ്. അപ്പോൾ ഈ ചാർജിൽ നിന്ന് വരുന്ന ഫ്ലക്സിനെ മൊത്തത്തിൽ എൻക്ലോസ് ചെയ്യണമെങ്കിൽ അതുപോലെ 1 2 3 4 5 6 7 8 ക്യൂബ് വേണം. അതുകൊണ്ട് ഈ ചാർജിൽ നിന്ന് വരുന്ന ഫ്ലക്സുകൾ എല്ലാം ഈ 8 ക്യൂബിലൂടെയാണ് കടന്നു പോകുന്നത്. അപ്പോൾ നമുക്ക് ഇതൊരു വലിയ ക്യൂബായിട്ട് സങ്കല്പിക്കുകയാണെങ്കിൽ ഈ ക്യൂബിൻ്റെ ഒരു വശത്ത് തന്നെ, ഒരു ഫേസിൽ തന്നെ ചെറിയ ക്യൂബുകളുടെ 4 ഫേസുകളുണ്ട്. അപ്പോൾ ഈ വലിയ ക്യൂബിൽ 6 ഫേസ് ഉള്ളത് കൊണ്ട് 6 × 4 24 ഫേസുകളുണ്ട് അവിടെ. Which means the total flux of the charge passes through these 24 phases. This flux through 24 phases, that is equal to Q by epsilon 0. അതായത് ഈ phi is the flux through one phase. One phase mean ഈ ചിത്രത്തിൽ ഇതുപോലുള്ള ഒരു ഫേസ്. Flux through one phase, and flux through 24 phases means 24 flux, 24 phi is flux through one phase is equal to Q by epsilon 0. Therefore flux through one phase, that is equal to Q by 24 epsilon 0. അപ്പോൾ നമ്മുടെ ഈ ക്വസ്റ്റ്യനിൽ ചോദിച്ചിരിക്കുന്ന ഈ ഒരു ഫേസിൽ കൂടി കടന്നു പോകുന്ന ഫ്ലക്സ് മീൻസ് that is Q by 24 epsilon 0 if the charge Q is kept to the corner of a cube. Okay, thank you very much.